So we're going to go over three major things: the gravity floor framing system, the lateral system, and the foundation design. So this is the introduction. So why did we choose this place? So first of all, existing there right now is the Trump Tower, and it's also right next to the Central Park, so it's a great tourist attraction. It's in Midtown Manhattan. There's many businesses there. It's a central business district. Many tourists there. There's a subway, nearby subway station, so it's easy access to major road facilities for commuting for employees and clients. And it contributes to the iconic cityscape, adding a modern touch to the skyline. And our architectural looking design really fits in for tourists because they come to look at nice skyscrapers, and ours is a nice design. Another reason we chose this location is because it has a level exposure of C, which was a better option because a lot of the other ones had an exposure of D. And it's exposed to varying wind speeds due to its urban landscape. And the tower's design must consider the local wind patterns and the potential impact on structural integrity. And the wind design data is taken from 1603.1.5. So here's some basic New York City building codes and structural criteria codes in general. So we have the New York City Building Code of 2022, the ASCE 7-05, and the ASCE 7-16. For structural steel, our building is in accordance with the AISC 360-16, and for concrete, our building is in accordance with ACI 318-14. Here are just some of the, I'm not going to read them, but some basic things that we snipped. We used a live load of 100 PSF, a construction load of 20 PSF, a dead load of 20 PSF, and a superimposed dead load of 20 PSF. So here are some basic footprints of the description. I'll go into this a little later, towards the end. So our dimensions are 150 by 100, and it's a 40-story high rise. And each floor is 15 feet for commercial use versus residence use, which is 12 feet. And our floor-to-floor height is efficient for structural design, accommodating utilities and architectural aspects. It's a total height of 600 feet, which was taken by multiplying 15 by the 40 stories. And the height of the tower poses challenges related to wind loads, lateral stability, and vertical load distribution, which you will also see later on. Okay, so first thing to notice here is we only have 4 different beam sizes used, which Christian will cover later, but it's essentially just to make it easier to build, and it's good for time effectiveness, but Christian will mention it soon. So we used 4 W21s by 55, 25 W18s by 40, 19 W16 by 31s, and 16 W10s by 12. Here are the basic materials we use, which are steel and concrete, and their self-weights are 490 pounds per cubic feet and 150 pounds per cubic feet. We chose steel because of its exceptional strength to weight ratio, and it reduces the dead load and construction costs. So we didn't use steel for most of it, obviously. It took about 15 to 20% of our material costs. And concrete provides compressive strength and stability. We chose the I shape because of its efficient material distribution, and it minimizes costs. Its resistance to bending, shear, and various load effectively, and it's adaptable to complex architectural designs.
So next we'll talk about our gravity floor framing system. So here's our original floor framing system. It was inspired by the Mercury City Tower in Moscow, Russia. We have a minimum column spacing at 30 feet from each other, and we have 40 to 45 depth spacing from the core walls. This is just standard design criteria. We use composite beams, which are beams that combine materials such as steel and concrete to create a structure with a higher load-bearing resistance and make it more suitable for heavier loads. As you can see in the drawing, originally all our beams were optimized to have a between 0.9 and 1.0 stress ratio. This was computed through ETABS. So ETABS doesn't take into consideration the construction of the actual tower. So it gives all the different beams, but with various different beams to get as close to the ultimate stress that it needs to withstand. So on our next slide, you can see here that not all of our beams are optimized, but they're more similar beams. So as John mentioned earlier, this changed our design from having various beams to only having 4 different beam types. This helps a lot during the construction of the tower. It makes it so less different variety of material has to be ordered. And we also made sure to change all the exterior beams to be uniform. This is also for construction reasons when building the facade. And we also changed our stress ratio from 1.0 to 0.9 for structural safety reasons. So for our metal deck, we had a concrete slab depth of 4.5 inches. This is just typical. It has, it's a normal weight concrete, and it's just to meet the design strength and to our rating. Our steel deck was an 18 gauge steel deck and 3 inches deep for our total slab depth of 7.5 inches. The maximum sheet length of our deck was 42 feet. During phase 1 of construction, the metal deck needs to support the weight of concrete and the construction loads. So the load combinations we used were 1.4 dead load and 1.2 dead load plus 1.6 construction live load. Once construction is completed, the slab needs to withstand permanent loads of the tower. So the load combination we used then were 1.4 dead load and 1.2 dead load plus 1.6 live load. An important thing to mention is the fire protection of the slab. So it has a 2-hour rating, which is a crucial safety requirement in building construction. This is just to ensure that in case of a fire, it will protect the elements for 2 hours until the fire spreads. This is essential for occupant safety and to prevent the spread of the fire within the building. And all structural steel should be fireproof, typically with spray-on material. So this is a steel deck that we chose to construct with. It's a Voltcraft 3 VLI 18. Voltcraft is the manufacturer of the steel deck. 3 is the inches of depth of the steel deck, and the 18 is the type of gauge that we use. As you can see on the diagram, we chose this deck because it's most suitable for the superimposed dead load of 20 pounds per square foot and the live load of 100 pounds per square foot. And as I mentioned earlier, it has a maximum sheet length of 42 feet. We also chose this because it's very strong, stable, and it's cost effective since it is a readily available material. It also meets the fire rating requirements for multi-story buildings. On the screen, you can see the 2 different sets of ETAB models. So on the left side of the screen is the live load analysis. On the top is the shear diagrams of our floor framing system, and on the bottom is the moment diagrams. On the right side of the screen, you can see the dead load analysis. Once again, on the top is the shear load, the shear diagrams, and on the bottom is the moment diagrams. So for our beam analysis, we chose to do a centralized beam, which was a W16 by 31. It composed of 36 studs and has a camber of 1.5 inches. So for our live load analysis, on the left side of the screen, this is the information that ETABS provided.
So for our lateral system, we did use concrete shear walls as well as lateral bracing. The effectiveness of concrete shear walls is influenced by the thickness, which varies based on floors. This is cost effective while meeting structural requirements, and it's also an efficient design for load distribution. The effectiveness of lateral bracing minimizes lateral displacement and drift, and it increases overall structural stiffness. And it also offers a cost-effective solution for stability and safety. So we did, for floors 1 through 20, we used the 28-inch wall and 9,000 PSI strength concrete. For floors 21 through 32, it's a 24-inch wall with a strength of 9,000 psi. And for floors 33 through 40, it's a 20-inch wall and a strength of 6,000 psi, as well as lateral bracing on floors 20 to 21, and that size is W24 by 94. We did make the thickest walls with the highest strength on the bottom because it will have higher loads. So this is the displacement for diaphragm. Our allowable displacement is H over 400, which is 600 feet times 12 inches per foot divided by 400, which gave us 18 inches. So our first design, we had just a 12-inch wall thickness with 4,000 psi. It gave us a really high displacement of 64.1 inches. So we did have to reconsider our design, and we ended up changing the concrete wall thickness as well as the strengths. And that gave us the 18.5-inch displacement, which was right over our allowable of 18. So we did add lateral bracing on floors 20 to 21, and that got us to 16.8 inches of displacement. So you can see that in our graph here, the allowable is the dashed line, and the 16.8 is just right under. So our effective design was able to reduce the displacement by 47.3 inches. And this is the ETABS model and also the animated ETABS model to show the displacement of 16.8 inches. So this is the shear force under ultimate wind load. The shear force diagram under ultimate wind load in both the X and Y directions for this building illustrates the distribution of lateral forces throughout its height. The presence of lateral bracing between floors 20 to 21 enhances the building's lateral stability, and that impacts the shear force diagram by redistributing and effectively managing the lateral forces induced by ultimate wind load. This first diagram is the wind load on the shear force diagram for the X direction, and the second is in the Y direction. As you can see where we have our lateral bracing, there is a jump in the shear force diagram. This is our moment under ultimate wind load. The moment diagram under ultimate wind load in both the X and Y directions for this building provides a visual representation of the distribution of bending moments across its height. The inclusion of lateral bracing between floors 20 to 21 is a key design element impacting the moment diagram. Lateral bracing enhances the building's resistance to lateral forces and effectively redistributes bending moments induced by ultimate wind load. So our first diagram is the moment in the X direction, and the second is in the Y direction. And as you can see, same as the shear, there is a jump in moment where we have our lateral bracing. So this is our column analysis. These diagrams illustrate the axial dead load acting on the columns. As you can see in the first diagram, there is an error in the analysis, which is evident there. The error results in a reduction in the dimensions of automatically selected columns, which is why we also realized that there was an error. Ideally, the load should incrementally increase as one descends through the structure, and this depiction is generated through auto sequence derived from a construction sequence grouping of 2, which is how we got our axial dead load second diagram. And utilizing auto sequence, we produce the visual representation where the axial load consistently heightens in a downward direction.
Right, so to go over the foundation design, this is our dead load plus live load soil pressure deflection diagram. And as you can see with the 0.75 factored in, as well as the wind load, they look practically identical. This is a 3D. So as you can see, all the pressure, the soil pressure, lies where the core is. And basically, that foundation distributes the building's weight evenly over a large area, and it provides stability against structural loads, including wind loads, seismic loads, and gravity loads. The soil bearing capacity we used was 20 KSF. The material was 6,000 PSI. We used a 96-inch slab depth, and that's pretty much it. So here's the shear stress diagram. So I'm just going to go over one or two of them. So in this corner here, we have 1.2 dead load plus 1.6 live load. And this is the XZ direction. So if you're looking at it from a safe kind of view, that means S13. So the 1, 2, and the 3 in safe were just X, Y, and Z directions. So in the S13 direction, which is the XZ direction, we had a maximum shear stress of 0.6166 kips per inches squared. And inside the brackets are just the coordinates, which you can clearly see by the colors that is where the core sits, as well as the minimum, which is a negative 0.6772 kips per inches squared, is also right next to it, but on the other side in the core. So all these pictures essentially are the same thing, just in different directions. So we did a 1.2 dead load plus 1.6 live load, which in safe was decon 2, and 1.2 dead load plus 1.0 live load plus 1 wind load was decon 11, and these are just the different pictures. Here's the reinforcement design. So we use a number 11 for the top and the bottom with a 6-inch spacing, and essentially we use 2 rebar in one spot, so we coupled the rebar. And these are just the directions, once again, X and Y for top and bottom. And I'm just gonna go over one of them again. So the max was 20.4149 inches squared feet at the coordinates, which were in one of the colored sections, and those are the coordinates. Same coordinates as the last picture, actually. And 0 is just the purple. So everything purple is just 0. And this is the reinforcement moment diagram. So this is the top rebar on the left and the bottom rebar on the right. Once again, we use number 11 at a 6-inch spacing, coupled. And the max moment at the top rebar was 11.044 inches squared per foot. At the coordinates, again, you could probably see where it is. And in the bottom, the maximum moment was 29.6794 inches squared per foot. And yeah, so we essentially got these by putting design strips on the X and Y coordinates. So that was the conclusion. So here's the material takeoff. So as I was saying before, the steel cost typically ranges from 15 to 20% of the total project. And you can see here, we used A992FY, which is a steel type material, for the column beam and brace. So we took all the weights in kit and we added them together to get 5,186.2 under the steel kit. And we divided that by 2 in order to get in tons. And then for concrete, we had for walls in 9,000 PSI and 6,000 PSI, as well as the floor in 4,000 PSI, and we added those together once again to get 59,691.6 kips. And if you're wondering what the 150 is, that's just the self-weight of concrete. So in order to convert it to feet per cube, we took 59,691.6, we multiplied it by 1,000, and then divided it by 150. So we got the feet per cube. And then we just converted that to yards per cube. So I could read the challenges here, but I'm just gonna go off of what we did technical. So the gravity system, which is the floor funding plan, we had a couple technical difficulties, like while running it, it would change the beams consistently against us. So that was one big problem. And then just, a learning curve in the beginning we had to face. For the lateral system, if you saw earlier, we had a bracing issue. So we had to change how much, originally we were gonna change from 9,000 PSI, we were gonna keep changing it. And as you saw the different designs for the displacement, and we decided to just put a bracing around the 25th floor, and that just cleared everything up. And then for the foundation, it was just a lot of confusion for the foundation, but we got through it. And there's no challenge without lessons learned, right? So every challenge we had was a lesson learned, but I think the biggest challenge that we can all agree on is that we didn't have enough time to learn Rhino and Grasshopper and E-tabs. And also, another big thing, I don't know if you noticed, but like the Infinity Tower, we plan, or like the Mercury Tower, we plan to shorten it after 20 floors and then create like a cool looking design, but of course we didn't have enough time. So we are gonna further our knowledge with this and expand on this. So I think that's another big lesson that we're gonna learn. And these are just our references.
That's all.
All right.